Go.
Hello classmates, my name is Mirasol.
And I'm Julissa.
And today we are going to talk about circular motion
Tori.
and gravitational force.
So today I will be explaining about circular motion, which the definition for circular motion is a motion along a circular path in which there is no change in speed, only a change in direction. For example, it's the water in a cup, which Mirasol will be demonstrating.
So here you can see I have a piece of cardboard that's wet and a cup filled with water and some string. You can see, well I can see, you can't see, but that when I move it, the water stays still, and if you use enough velocity or speed, you'll be able to do a 360 degrees without the water spilling. And so, do it like that. Oh my god, scary. So here I have a string and an eraser, and this is another way to demonstrate circular motion. So what is happening is that there's a constant velocity towards the direction of the path, and there's also a constant force towards the center. And let's say if the string were to break, or if I were to let go of the string, what would happen? So what happened is I let it go here, and it kept on going in the same path. Like I said earlier, that it was tangent, and that's how it went. Whoop. So here we have a problem for circular motion. A 300-kilogram go-kart moves at a constant speed of 20 meters per second around a circular track. If the distance from a car to the center of the track is 50 meters, what is the centripetal acceleration and the force of the car? So to solve this problem, we actually would use a formula for centripetal acceleration, and that formula is written in this way. So this is step 1. And so we would use the given. So we would use the given. And the given is 20 meters per second. We would square it over the radius, which is 50 meters. And that equals to 400 meters squared over seconds squared over 50 meters. To simplify this, the m's would cancel, and 400 divided by 50 would be 8 meters per second squared. And that's the answer to the first. In order to find the centripetal force, we would use the formula centripetal force equals mass times acceleration. And we would also use the given, which would be 300. And the acceleration, we got it from the first step, so it's 800, and you would include it. 8 meters per second squared. And you'll get a result of 2,400 newtons. Is a twist or turn that tends to produce rotation. So, for example, turning a doorknob. It's twisting, rotating. And it's also a force that causes change in rotational motion and produced when a force is applied with leverage. So, for example, a claw hammer to pull a nail from a piece of wood, and also a seesaw, and Julissa will demonstrate this.
So as you can see here, we have a wannabe teeter-totter, and the objects we have is the tech deck and the skull. So if I were to put the tech deck all the way at the end of the ruler and put the skull on the other end, as you can see, it's not balanced. So in order to balance it out, we would have to move the tech deck until it equally gets balanced. So as you can see right there, it gets somewhat balanced to it. So for example, a 20-kilogram girl is sitting 3 meters from the center of the teeter-totter. How far must a 50-kilogram boy sit from the center in order to be balanced? So I'm going to draw out the teeter-totter. And here, I don't know, draw good. Here's a girl, and here is a boy. Let's break here. So the girl is 20 kilo, and she is 3 meters from the center, and the boy is 50 kilogram, and we don't know how far he is from the center. So the equation we will use is T equals T. It could also be known as FR equals FR. And in order to solve this equation out, we will have to find the weight of the girl and the boy. So weight equals mass times gram. So it's 20. Oh no, it's gravity. Sorry. So it's 20 times 10, which it would equal 200 newtons. And for the boy, you do the same thing. So it's 50 times 10, which equals 500 newton. And now that we have that solved in, we are able to now plug in to solve the problem. So this is for the girl, this is for the boy. So it's 200 newton times 3 equals 500. And we don't know what the radius is, so we leave it just R. So 200 times 3 would be 600 equals 500, or divided by that, so we could find out the radius, and we would get 1.2 equals m, which is equal to the radius. So the 1.2 would be right here. So 1.2 meters would go right there, and that's how we figure out how to solve where the boy has to sit to be.
Gravitational force is Newton's law of gravity, states that the gravitational force between two bodies is proportional to the product of their masses and inversely proportional to the square of the distance between them. For example, the distance between Earth and its moon. So you can see here this.
So an example would be, determine the force of gravitational attraction between the Earth and the moon. Their masses are 5.98 times 10 to the 24th power kilograms and 7.26 times 10 to the 22 power kilograms, respectively. The average distance separating the Earth and the moon is 3.84 times 10 to the 8 power meters. So for this equation, we would use F equals G mass 1 times mass 2 over the radius squared. So we know that G is always going to be 6.67 times 10 to the negative 11 power. And then we're gonna plug in our first mass, which is 5.98 times 10 to the 24. And now we're gonna plug in our second one, which is 7.26 times 10 to the 22, divided by, we're going to do all of that with the distance between the moon, so it's 3.48 times 10 to the 8th power, but we're going to square it. So then we're going to get our calculator, and we're going to plug in all of that. So we're going to put parentheses 5.98. So what I did on the calculator is I plugged in these two numbers and divided by the bottom. So we got 2.944 and etc. So press multiply, right? So now what we're going to do is multiply the answer to the gravity. So times parentheses 6.67 times 10 to the power of negative 11 equals 1.96 times 10 to the 20th power.
Here I have 3 cups filled with water halfway, and a cardboard and some string. What I would like to show you is you can see that the waters are staying still and not moving, and the cups are not spilling. I can kind of feel it, but okay. And so now I'm going to do a 360 and hopefully it doesn't spill. So here I have a ball and a string. Well, it's actually a lemon. Same thing.